On February 26, 2026, satellites orbiting far above the Southern Ocean recorded something researchers were not fully prepared for. Antarctic sea ice had shrunk down to 258 million square kilometers, its lowest point of the year. That number on its own sounds like just another data point in a long string of climate statistics. But sit with it for a second, because the context is what makes it strange. That figure placed 2026 as the 16th lowest minimum in 48 years of satellite records, which sounds almost unremarkable, until you realize it came directly after 4 consecutive years of the most extreme sea ice collapses ever measured around Antarctica. The ice had been vanishing at a pace that alarmed nearly every polar scientist on the planet, and then, almost without warning, it stabilized. Not fully recovered, but stabilized enough that researchers were forced to ask a question they hadn't expected to be asking in 2026. Was Antarctica pulling back from the brink, or was this simply the calm silence before something worse? At almost exactly the same time, on the opposite side of the globe, the Arctic was telling a completely different story. On March 15, 2026, Arctic sea ice reached its winter peak, expanding to 29 million square kilometers. That number might sound large, and in absolute terms it is, because winter ice in the north always dwarfs the summer minimum in the south. But when scientists at NASA and the National Snow and Ice Data Center compared it to history, they found themselves staring at a tie. Not a new record low, but a statistical tie for the lowest winter maximum ever recorded, since satellites started watching the poles in 1979. It matched almost exactly the previous year's low of 31 million square kilometers. 2 years in a row, the Arctic had failed to build back the ice that used to define its winters. 2 poles, 2 different signals, both breaking from the pattern scientists thought they understood. That is where the story begins, and it does not get simpler from here. To understand why these 2 numbers matter so much, you have to understand what each pole was expected to do. For decades, the Arctic and the Antarctic have behaved like 2 very different patients under the same global fever. The Arctic has been the poster child of climate change, warming at roughly 4 times the global average rate, a phenomenon researchers call Arctic amplification. Its sea ice has been declining more or less steadily since satellite monitoring began, with the summer minimum shrinking dramatically over the past several decades. Antarctica, by contrast, spent years looking almost stubbornly unaffected. Through the 2000s and into the early 2010s, Antarctic sea ice actually grew slightly in some years, defying the warming trend elsewhere and giving skeptics a talking point and scientists a genuine puzzle. Then, in 2015, something flipped. Antarctic sea ice stopped expanding and began a decline so sharp that by 2023 it had crashed to a record low of just 691,000 square miles, an area of missing ice larger than the entire island of Greenland when compared to the historical average. For years, nobody could fully explain why the frozen continent that had seemed protected suddenly became vulnerable. That mystery sits at the center of everything that happened in 2026. Let's start at the bottom of the world, because the most detailed scientific detective work this year happened there. In May 2026, a team of researchers led by scientists at the University of Southampton published a study in the journal Science Advances that finally pieced together what triggered Antarctica's collapse. They described it, almost poetically, as a triple whammy of climate chaos, a phrase that captures both the complexity and the severity of what they found. The story starts decades before 2015, with the strengthening of the westerly winds that circle Antarctica. Those winds have been intensifying for years, partly because of the buildup of greenhouse gas pollution from burning fossil fuels, and partly because of the hole in the ozone layer above the continent, a separate but related atmospheric wound. At first, these stronger winds actually helped cool the surface ocean around Antarctica. That is part of why the ice held on for so long, resisting the warming trend that was reshaping the Arctic. But climate systems are rarely static, and what looked like protection was actually the first phase of a much longer chain reaction. By around 2015, the second phase kicked in. The same winds that had once helped cool the surface began dragging up warm, salty water from deep in the ocean, hauling it toward the surface where it could finally make contact with the ice above. This deep water had been sitting below the surface for a long time, insulated from the atmosphere, carrying heat that had nowhere to go. Once the winds pulled it upward, that stored heat began melting sea ice directly. And here is where the physics gets genuinely unsettling. As the ice melted, it released fresh water, but the winds were also bringing up saltier water from below, and that extra salt made the surface layer denser. Denser surface water mixes more easily with the layers beneath it, which allowed even more of that warm, deep water to rise up and continue the melting. It was a feedback loop building on itself, each stage making the next stage easier. Then, around 2018, the third phase locked the whole system into place. With less sea ice covering the ocean, the surface water stayed warmer and saltier than it used to, because there was no longer a thick lid of ice keeping the layers separated and stable. And that warm, salty surface water made it even harder for new ice to form in the first place. The system had essentially trapped itself in a cycle where low ice conditions actively prevented the return of high ice conditions. One of the study's authors, Aditya Narayanan, a research fellow in physical oceanography, described it as a demonstration of how long-term changes driven by climate change can trigger a cascade of processes that push an entire system toward a prolonged state of low sea ice. In plainer language, Antarctica did not simply get warmer and lose ice in a straight line. It crossed a series of thresholds, each one making the next one more likely, until the whole regional system reorganized itself into something new. Interestingly, the researchers found that the story wasn't identical on every side of the continent. In East Antarctica, the sea ice retreat was mostly driven by that deep ocean heat rising up from below. In West Antarctica, the atmosphere played a bigger role, with warm air carrying clouds that trapped heat closer to the ocean surface. Two different mechanisms, converging on the same outcome. And the consequences of that outcome ripple outward in ways that go far beyond the ice itself. When sea ice disappears, it leaves the massive ice sheets and glaciers along Antarctica's coastline directly exposed to ocean waves and warmer water, which makes them dramatically more vulnerable to melting and breaking apart. Sea ice normally acts like a mirror, a bright reflective barrier bouncing the sun's energy back into space before it can be absorbed. Strip that mirror away, and you expose the dark ocean underneath, which absorbs far more solar energy, which warms the water further, which makes it even harder for ice to reform. It is the same kind of self-reinforcing loop showing up again, just operating at a planetary scale rather than a regional one. Perhaps most concerning of all, the researchers warned that the loss of sea ice could destabilize entire ocean currents, the ones responsible for storing enormous amounts of heat and carbon deep in the sea. If that stabilizing function breaks down, the Southern Ocean, which has quietly been one of the planet's most important buffers against climate change, could stop playing that role. Alberto Naveira Garabado, another author on the study and a physical oceanographer at the University of Southampton, put it in stark terms. If low sea ice conditions persist into 2030 and beyond, he said, the impacts could be enormous because the ocean around Antarctica could transition from being a stabilizer of the world's climate into a powerful new driver of global warming instead. Scientists who were not involved in the research echoed that concern. Ted Scambos, a senior research scientist who has studied polar ice for years, said the new study creates a far more coherent explanation for the past decade of Antarctic sea ice changes, and added that he now believes it is unlikely Antarctic sea ice will recover to what it once was. Oscar Schofield, a biological oceanographer at Rutgers University who also was not part of the research team, called the observed declines stunning, and said that understanding the drivers behind them will help researchers forecast the future with more confidence, even if that future looks troubling. So where does that leave the near average minimum recorded in February to 2026, the number that opened this story? Scientists at the National Snow and Ice Data Center were careful not to read too much into it. Walt Meyer, a scientist there, explained that this year's return to less extreme conditions was not entirely unexpected, given how much Antarctic sea ice naturally varies from year to year in the satellite record. In other words, one calmer year doesn't undo a decade-long trend, and it doesn't contradict the triple whammy mechanism the Southampton team identified. In fact, researchers pointed to a very specific short-term cause for the slightly higher 2026 minimum. Ted Scambos noted that through most of the year, Antarctic sea ice remained well below its historical daily average, but then in January and February, unusually strong winds blowing from the south pushed sea ice outward in the Weddell Sea, temporarily slowing the overall decline and nudging the minimum closer to normal. It was weather, essentially, giving the ice a brief reprieve, not climate reversing course. And the National Snow and Ice Data Center added an important caveat when they released the figure. The 2026 number was preliminary, and continued melt conditions or strong onshore winds could still push the extent even lower before the season fully closed out. The takeaway from Antarctica in 2026, then, is not that the crisis has passed. It's that scientists finally understand the machinery driving it, and that machinery, once triggered, does not appear to reverse itself easily. Now let's cross back over to the top of the world, because the Arctic story in 2026 turned out to be just as unsettling, even though the headline numbers looked at first glance almost stable. Remember that tide record low from March, the 29 million square kilometer maximum that matched the previous year's rock bottom peak. For a moment, some observers wondered if this represented a kind of plateau, maybe even a sign that Arctic ice loss was leveling off after decades of decline. That interpretation turned out to be dangerously premature, and a piece of research published in July 2026 explains exactly why. For years, there had been a genuinely puzzling pattern buried in the Arctic winter data. Between roughly 2005 and 2024, the rate of winter sea ice loss appeared to weaken. Ice was still declining, but more slowly than climate models expected, even as global temperatures kept climbing. That mismatch confused researchers because it seemed to run counter to everything else happening in a warming Arctic. Some scientists wondered whether some kind of natural stabilizing mechanism was kicking in, something that might be slowing the long-term trajectory of ice loss. A team led by researcher Duo Chan decided to dig deeper into that apparent pause, reanalyzing the latest satellite observations covering the Arctic's winter growth and peak periods. What they found upended the earlier, more hopeful interpretation entirely. The slowdown observed between 2005 and 2024 was not a sustained shift in the Arctic's trajectory. It was temporary. And the reason it looked meaningful for so long is that the data hadn't yet caught up with what came next. Once the exceptionally low ice levels of 2025 and 2026 were folded into the analysis, the entire picture changed. The apparent pause turned out to be nothing more than a lull, a brief and misleading quiet spell within a much longer uninterrupted decline tied directly to global warming. In other words, for nearly 2 decades, scientists and the public alike may have been reading short-term noise as long-term signal, and the last 2 winters corrected that mistake in the most dramatic way possible, by shattering the pattern that had seemed to be holding. The scale of what happened in the winter of 2025 to 2026 becomes even clearer when you look past the headline maximum number and into the details researchers were tracking day by day. According to the Met Office, Arctic sea ice extent for March 2026 was the lowest ever recorded for that month, coming in at 17 million square kilometers, narrowly below the prior year and dramatically below the 1981 to 2010 average of 43 million square kilometers for that same month. The single highest daily extent recorded all winter, which occurred on March 7th, was also the lowest daily maximum ever measured, at 34 million square kilometers, compared to a historical average daily maximum of 65 million square kilometers. That gap, more than 1 million square kilometers of missing ice compared to what used to be normal, is difficult to visualize, but researchers offered a comparison that helps. According to the National Snow and Ice Data Center, the 2026 maximum extent came in 36 million square kilometers, smaller than the 1981 to 2010 average, an area roughly equivalent to twice the size of the entire state of Texas, simply missing from the top of the world. And the geography of where that ice failed to form tells its own story. The Met Office reported that extent was particularly low all along the Atlantic side of the Arctic Ocean, in the Labrador Sea, the Greenland Sea, and the Barents Sea, regions that have become some of the most sensitive front lines of Arctic change. The Sea of Okhotsk was also exceptionally low. Curiously, the Bering Sea bucked the trend slightly, showing near average or even above average ice for parts of the season, a reminder that even within a record-breaking overall decline, the Arctic doesn't change uniformly everywhere at once. Some regions are transforming far faster than others, and that regional variability is itself something scientists are trying to understand, because it shapes how quickly different coastal communities, ecosystems, and shipping routes will feel the effects. Dr. Letty Roach, a polar climate scientist at the Alfred Wegener Institute, described the past 6 months leading into that record, tying maximum as a period when Arctic sea ice extent sat at record or near record lows, alongside unusually warm conditions across much of the region. She explained that these 2 things go hand in hand because warmer air and ocean temperatures help melt the ice, and with less ice present, the ocean absorbs more heat directly from the sun, which in turn speeds up the warming even further. It's the same reflective mirror effect described earlier in Antarctica, just playing out at the opposite pole. Roach also pointed out something that doesn't show up if you only look at the extent numbers: the flat, 2-dimensional measurement of how much area is covered by ice. Arctic sea ice, she said, isn't just shrinking in extent, it is also becoming much thinner and more fragile than it used to be. Thinner ice melts faster, breaks apart more easily, and offers less insulation between the ocean and the atmosphere. That thinning trend was backed up by hard numbers from another polar researcher, Zachary Labe, who described the winter of 2025 to 2026 as grim news for anyone tracking the health of the Arctic ice pack. He noted that sea ice near the North Pole itself had shown record low thickness for several consecutive months, and that in February 2026 specifically, the total volume of Arctic sea ice, not just its surface area but its actual 3-dimensional mass, was the second lowest ever recorded. Volume matters enormously here because an ice sheet can technically cover a large area while still being dangerously thin and fragile underneath, the frozen equivalent of a house that looks fine from the street but is quietly rotting from the inside. Labe cautioned that it was still too early to say exactly what this weak winter peak would mean for the coming summer melt season, since regional weather patterns can shift quickly and unpredictably. But he was clear about the broader signal. The winter of 2025 to 2026, he said, stood as another unmistakable indication of just how fast the Arctic is shifting beneath our feet, or rather, beneath the ocean's surface. And then there is a discovery from the Arctic in 2026 that may end up being the most consequential of all, even though it received far less mainstream attention than the ice extent headlines. In late May, researchers published a study in the journal Communications, Earth and Environment, revealing that the Arctic Ocean appears to have crossed a chemical tipping point, one that could permanently reshape the base of the entire marine food chain. The research was led by scientists at the University of Edinburgh, working alongside institutions including the Norwegian Polar Institute, the Scottish Association for Marine Science, the Technical University of Denmark, and the Alfred Wegener Institute in Germany. Their work drew on more than 2 decades of ocean sampling data, collected between 1998 and 2023, gathered in the Fram Strait, the narrow but critically important passage between Greenland and the Norwegian archipelago of Svalbard, through which much of the Arctic Ocean's outflow passes on its way toward the Atlantic. For years, the conventional expectation among scientists was straightforward. As sea ice disappeared, more sunlight would reach the ocean's surface underneath, and that extra sunlight would fuel more photosynthesis, more phytoplankton growth, and ultimately a healthier, more productive marine food web. It made intuitive sense. Less ice covering the water should mean more light, and more light should mean more life. But the new research found that this relationship has fundamentally broken down, in a direction nobody had fully anticipated. Marta Santos Garcia, a doctoral researcher at the University of Edinburgh, who co-led the study, explained that the team's findings suggest the Arctic Ocean has shifted from a system that was mainly limited by available sunlight to one that is now increasingly limited by the availability of a completely different resource, nitrate. Nitrate is one of the essential nutrients that phytoplankton, the microscopic algae sitting at the very foundation of the marine food chain, absolutely require in order to grow. Here is the mechanism the researchers uncovered, and it's a genuinely surprising piece of chemistry. As sea ice retreats from vast, shallow coastal regions of the Arctic Ocean, those areas become newly exposed to direct sunlight for the first time in the seasonal cycle. Sometimes, for the first time in generations, that sunlight does trigger a burst of phytoplankton growth right at the surface, just as the old model predicted. But when those phytoplankton eventually die, they sink down to the shallow seafloor beneath them, where a completely different community of organisms, bacteria and single-celled archaea, break the organic material down. In the process, they intensify a natural process called benthic denitrification, a chemical reaction that converts nitrate into nitrogen gas. That conversion is the critical twist, because nitrogen gas is essentially useless to most marine plankton, which cannot absorb it directly the way they can absorb nitrate. So this process permanently strips a usable nutrient out of the water and replaces it with something the ecosystem largely cannot use, a one-way chemical exit ramp for a nutrient that used to cycle and recycle through the system. Researchers trace this shift back to a surprisingly specific point in time, around the year 2009. According to the study, nitrate concentrations in what's known as the polar surface water flowing out through the Fram Strait dropped sharply after that year and have remained persistently low ever since. Professor Raja Ganeshram of the University of Edinburgh, who led the broader research effort spanning nearly 2 decades, said the changes documented in the study suggest the Arctic Ocean ecosystem passed a genuine tipping point around 2009. He emphasized that how this shift eventually cascades through the food chain needs to be watched extremely closely because the implications are profound, including for commercial fishing operations far to the south in the North Atlantic Ocean, an industry that supports coastal economies well beyond the Arctic itself. The research team identified the Chukchi Sea and the East Siberian Shelf as the 2 primary zones where this nitrate removal is occurring most intensively. By their estimates, those 2 relatively shallow shelf regions alone are removing something in the neighborhood of 12 teragrams of nitrogen from the ocean every single year, a volume large enough to offset a substantial portion of the nutrients that would otherwise be flowing into the Arctic from the Pacific Ocean. And the consequences of losing that nitrate ripple outward through every level of the food web. Larger, more nutrient-dense plankton species, like diatoms, are highly efficient at transferring energy upward, from plankton to zooplankton, from zooplankton to fish, and from fish to the larger predators, birds, and marine mammals that depend on a healthy, energy-rich food supply. When nitrate becomes scarce, smaller plankton species gain a competitive advantage over those larger, more nutritious varieties because they can survive on lower nutrient concentrations. The problem is that these smaller plankton are far less efficient at passing energy up the food chain. The base of the pyramid doesn't just get smaller, it gets structurally worse at supporting everything built on top of it. The consequences extend beyond biology and into the planet's carbon cycle as well. Phytoplankton play an outsized role in capturing carbon dioxide from the atmosphere through photosynthesis, a natural process that helps buffer the pace of global warming. If nitrate scarcity limits how much phytoplankton the Arctic Ocean can support going forward, that could measurably reduce the ocean's capacity to store carbon, removing one more piece of the planet's natural climate regulation system right at the moment it's needed most. And unlike some climate changes that could theoretically be reversed if emissions dropped sharply, the researchers behind this study were notably pessimistic about reversibility here, because the shift in nutrient conditions is being driven directly by ongoing sea ice loss, and because the underlying chemistry of benthic denitrification has already been triggered across such a wide area, the scientists concluded it is very unlikely the Arctic Ocean will ever revert back to its previous chemical state, even under the most optimistic future emission scenarios. It's a genuinely rare kind of finding in climate science, a change that isn't just severe, but appears to be functionally permanent on any timescale that matters to us. For communities that depend on Arctic marine ecosystems, both wildlife and the indigenous peoples who have lived alongside these waters for generations, these changes are not distant, hypothetical projections buried in a scientific journal. They are unfolding in real time, showing up as declining fish population productivity, shifting migration patterns among marine mammals that have followed predictable routes for centuries, and a visible transformation of ecosystems that once seemed almost timeless. Researchers noted that further work is needed to fully understand how these Arctic Ocean changes might ripple outward into other parts of the world's oceans, including the North Atlantic, where commercial fishing fleets depend on nutrient flows that originate, in part, from these now disrupted Arctic waters. So step back for a moment and look at the full shape of what happened at both ends of the planet in 2026, because the pattern that emerges is more unsettling than either story would be on its own. In the Arctic, ice that briefly appeared to be stabilizing turned out to be doing nothing of the sort. Its apparent pause revealed as a temporary lull inside a longer, accelerating decline, while underneath the surface, an invisible chemical transformation was quietly and perhaps permanently rewriting the rules of the entire marine food web. In Antarctica, a slightly less extreme minimum, one that on paper looked almost reassuring, actually sat on top of a newly understood mechanism, a three-stage feedback loop of wind, warm water, and salinity that scientists now believe may be extraordinarily difficult, if not impossible, to reverse. Two poles, two very different sets of numbers, and yet the same underlying story, systems that spent decades absorbing change quietly, only to reach thresholds where the change started reinforcing itself. What makes 2026 genuinely significant isn't a single dramatic headline number. Both the Arctic maximum and the Antarctic minimum were, in isolation, fairly close to recent years, not the most extreme values ever recorded. What makes this year significant is the explanatory science that arrived alongside those numbers, research that finally connected the dots behind years of confusing, sometimes contradictory observations. Scientists now have a coherent mechanical explanation for why Antarctica flipped from resilience to rapid decline starting around 2015. They have direct evidence that the apparent slowdown in Arctic winter ice loss was an illusion created by incomplete data rather than a genuine change in trajectory. And they've identified a specific chemical process, quietly operating beneath the visible ice loss in the Arctic, that may have already locked in a transformation of the ocean's food web that no reduction in emissions can undo. None of this means the story is finished, or that every remaining question has been answered. Researchers are careful, appropriately so, to note the uncertainties that remain. The National Snow and Ice Data Center flagged the Antarctic minimum as preliminary, subject to revision if late-season melt or wind patterns pushed it lower. Polar scientists studying the Arctic acknowledged it was still too early to say exactly how the historically weak winter maximum would translate into the coming summer melt season, since short-term weather can still shift outcomes considerably. And the researchers tracking Arctic ocean nitrate levels emphasize that further monitoring is essential to understand exactly how this cascading disruption will play out across different species, different regions, and different timescales in the years ahead. But taken together, the events of 2026 mark a meaningful shift in how scientists understand polar change itself. For a long time, the dominant narrative was fairly linear. Warming causes ice loss causes more warming, and the process simply continues at a steady, if concerning, pace. What emerged this year at both poles was something more complicated and, in some ways, more alarming. Evidence of thresholds, feedback loops and tipping points, moments where a system doesn't just change gradually but reorganizes itself into a fundamentally different state, one that resists returning to how things used to be. The Antarctic's triple whammy of winds, warm water, and salinity. The Arctic's chemical transformation from a light, limited to a nitrate-limited ocean. These aren't just two more data points in a long-running climate story. They represent scientists catching, in real time, the moment two of Earth's most remote and least visited regions crossed lines that may not be crossable in reverse. It's worth pausing on just how differently these two regions have historically behaved, because that contrast is part of what makes 2026 so striking. Antarctica sits on a continent, a huge mass of rock and ice more than 5,000 meters thick in places, surrounded by ocean. The Arctic, by contrast, is essentially an ocean surrounded by continents, a thin skin of frozen seawater floating on open water rather than resting on solid ground. That structural difference is a big part of why the two poles have responded to warming on such different timelines. Sea ice floating on open ocean is inherently more exposed to shifts in ocean currents, wind patterns, and water temperature than ice sitting on top of a landmass, which is one reason the Arctic began its visible decline decades before Antarctica showed any comparable signal. For years, that difference gave rise to a kind of false reassurance around Antarctica, an assumption that its sheer size and its different physical setting might insulate it from the same fate. The 2026 research effectively closes the door on that assumption. It shows that once the right combination of wind strength, ocean stratification, and heat transport aligns, even a system as large and seemingly stable as the Southern Ocean can pivot into a self-reinforcing decline within the span of a single decade. There's another thread running through this year's polar research that's easy to miss if you're only looking at ice extent numbers, and that's the question of timing. The Antarctic triple whammy took roughly a decade to fully lock in, beginning with strengthening winds years earlier, moving through the upwelling of warm water starting around 2015, and finally closing into a self-sustaining feedback loop by about 2018. The Arctic Ocean's nitrate collapse traces back even further to a threshold crossed around 2009, nearly 2 decades before scientists fully recognized what had happened. In both cases, the visible consequences, low sea ice extents, disrupted marine ecosystems, arrived years after the underlying mechanism had already been set in motion. That lag matters enormously, because it means the full effects of changes already locked in today may not become fully visible for years to come. Scientists studying both regions have started to describe this as one of the more unsettling aspects of polar climate science generally, the recognition that by the time a trend becomes obvious enough to make headlines, the mechanism driving it may already be a decade old and functioning on its own momentum. That lag also explains why researchers have been going back through older datasets with fresh eyes, trying to catch these transitions earlier next time. The Arctic Ocean nitrate study relied on 25 years of painstaking chemical sampling in the Fram Strait, data that had to be collected and compared across decades before the 2009 threshold became visible at all. The Antarctic sea ice study drew on satellite records stretching back to 1979, layered with newer measurements of ocean temperature and salinity that only became available in recent years through advanced monitoring networks. In both cases, the discoveries reported in 2026 weren't really about brand new events happening in real time. They were about scientists finally having enough historical data and computational power to look backward and recognize a pattern that had been building quietly for years. That's a sobering thought in its own right. The idea that some of the most consequential shifts happening on this planet might currently be running invisibly beneath data sets that simply haven't been analyzed closely enough yet to reveal them. And that, in the end, is what happened at both ends of the planet this year. Not a single dramatic collapse captured in one headline number, but a quiet convergence of research finally explaining mechanisms that had puzzled scientists for years, arriving at almost exactly the same time. From two regions 11,000 kilometers apart, each pointing toward the same uncomfortable conclusion, that the systems regulating ice at the top and bottom of our world may have already begun reorganizing themselves into something new, something scientists are still racing to fully understand, and something the rest of us are only beginning to grasp the scale of.